Good afternoon. So for this short talk, I'm going to talk about real quantum error correction. So the errors that happen in a code are the expression of the action of a unitary complex matrix. So our main will be to know what happened if we only consider real errors. Will it be necessary to go to the complex world to correct real errors? So for example, if we have some information encoding certain vectors to the space, if we send that information through a quantum channel and the passage through this channel can alter the code. Thus, a subspace C of a Hilbert space is a quantum error correcting code if and only if there exists an operator R such that for every vector in C we have this. Now it's like R can correct all the errors that Q may produce. Well, so our main is to build correctable subspaces. For this, we are going to study the error that can appear in a code. In the case of the qubit, there are two prominent errors, the bit flip and the base flip, which are X and C matrix. We know that X, C, and Y and the identity are a base for the 2x2 complex matrix, where Y is this product here. So we are going to focus on correcting these errors, because if we can correct these kind of errors, then we can correct all the linear combinations. So let's define the Pauli group PM. Is the multiplicative group generated by the matrix X, Y, C, and I by the identity. Actually, this is only the Pauli matrix together with the multiplies by plus and minus 1 and plus and minus I. And we define an element of Pn as a tensor product of n matrix in P1. Observe that Pn acts on the space of n qubits, and also we have that if we have two elements in Pn, then we have just two possibilities. They commute or they anti-commute. Okay, to continue with this talk, we must introduce some notation. So for example, in Pn, the element x sub I is going to be the tensor for which in all positions is the identity matrix F set in position number I, where is the X matrix. In the same way, we can define X sub I, C sub I, and Y sub I. And we also have that every Pauli operator can be written in this way, okay, using two bit strings of length n and a phase factor eta, where, as you can see in the example, the first string indicates in which position there are X matrix, and the second string indicates in which positions there are C matrix. So for this Pauli group, we have that the center is the multiplies of the identity, and if we make this quotient, we have the field of two elements to the end. So this quotient is a vector space, and we can work with it much better than with the group because it's going to be easier. So the first things that we can note of this vector space is that it's a symplectic space. So if you have P and Q cosets, the symplectic form lambda looks like this. Lambda is 0 if P and Q commutes, and is 1 if P and Q anti-commutes. So in fact, this symplectic structure is what will lead us to the construction of correctable subspaces. That's why it's so important. So to do this, to construct correctable subspaces, we will first study the symplectic transformations. So going ahead a little bit, I'm going to tell you that these symplectic transformations will be induced by a Clifford operator. And what is a Clifford operator? Okay, A Clifford operator is a unitary operator, yeah, that acting in the following way on the Pauli group results again in the Pauli group. Of these Clifford operators, there are three which are widely used in quantum computation, which are the following: Hadamard gate, phase gate, and control signal gate. The Hadamard gate and the phase gate usually acts on P1, and the control signal gate acts on P2. But we can generalize these gates, and we can make that they act on Pn. So, for example, if we are in Pn, we just define H sub I like, sorry. We define H sub X like acts like the identity on the all the tensor steps in the position I, where it acts like H gate, of course. And in the same way, we can generalize the operator S and the operator C naught. Okay, so there are two important things. Firstly, every Clifford operator induces a symplectic transformation like this. But something even more important is that every symplectic transformation is induced by a Clifford operator. And this Clifford operator is just a product of operator of the types H, S, and C naught. When I say type, I mean the generalizations of this kind of operators on PM. Okay, so now, as we are going to work in the quotient, it's important to define how the quotient acts on an NQA. For this, we will use our Clifford operator. So if the quotient of P belongs to an isotropic space, then as the action of the symplectic transformation is transitive on isotropic space, that means that there exists a Clifford operator U such that U by P by U dagger belongs to the same quotient of an element whose positions are only the identity matrix and X matrix. That is that they are equal except by a phase factor. Thus, we define the transformation, we define the transformation like this. We just take the vector, we add P, and then we just multiply by the phase factor eta. The interesting thing here is that defining the transformation like this, the n-qubit spaces is a representation of the isotropic space W. So, for example, the representation that corresponds to the isotropic space generated by all the cosets of the form X sub I is actually the regular representation. This is going to be actually a very important example. Okay, so now if we remember some of representation theory, we know that when the group is abelian, that of course is our case because Pn is abelian, the vector space is a direct sum of the InGen spaces. So if W is an L-dimensional isotropic space, then the space of n qubit is a direct sum of its InGen spaces, and each one will be of dimension 2 to the n minus L. So with this theory, we can actually prove the theorem that, okay, is we have a L-dimensional isotropic space, and we suppose that for any two operators, P1 and P2 belongs to E, that is a subgroup of Pm, we have that the product P1 by P2 belongs to W or does not belong to the orthogonal complement, then every InGen spaces of the qubit space, of course, we are seeing this space like a representation of W, is a error correcting code. Okay, so our purpose was to find subspaces that are protected against some kind of error. And now the problem turns to look the subspaces that are engine spaces to our representations. To make it easy, we are going to take a subspace V of the space of n qubits, and we are going to define the stabilizer. So it's going to be the subgroup of Pn, which acts like the identity on B. Okay, so maybe a weaker version, but in many ways is better, of the privilege theorem will be the following. We take a subspace V and we consider the stabilizer S. So S acts like the identity on B, but does mean that B is containing in the engine space of S, where S acts like the identity. Thus, we have that for a set of errors, whose double products belongs to S or do not belong to the normalizer, then we say that B will be correctable, will be a quantum error correcting code. Okay, so all of this is the way that we study quantum correcting error codes. Okay, so now we remember our questions. That was, what happened if we consider only real errors? Also, to answer this, we are going to consider just the real Pauli group, RP1, that is the multiplicative group generated by the matrix X and C. And we define the n real Pauli group, and an element of this group is going to be an n tensor, where in which position there is a real Pauli matrix. An important structural difference between Pauli group and real Pauli group is that the real Pauli group is a extra special to group. Then its quotient is endowed with a quadratic form Q, which in our case looks like this. Q of P is 0 if P squared is the identity, and Q is 1 if P squared is minus the identity. So something that we need to observe is that the quotient of the Pauli group, of the real Pauli group, is actually the same. And in fact, the bilinear form that determines our quadratic form Q is the symplectic for lambda that we have been talking about all this time. So the work that we did before with the symplectic form, we will do it again, but now with the quadratic form. Okay, so in the first place, we are going to study the orthogonal transformations. The orthogonal transformations are a subset of the symplectic transformation, and actually have this theorem that say that to generate the orthogonal transformation, we only need operator of type H and C0. So at this moment, in the real context, everything is behaving very well, because precisely the Clifford operator that we no longer need are the generalization of the phase gate, S gate, that actually is a complex matrix now. Like Hadamard gate and control CNOT are real matrix. So the first gate is the only one that we can take the real Pauli group to the Pauli group, maybe with complex things. So, I mean, we don't need complex matrices in the real errors world. So in this situation, where we only need real Clifford operators, we can define the action of the coset on a qubit in a much simpler way. So we will define as following. The element P is an element like this, of course, and we are going to define the transformation of the coset just ignoring the scalar eta, the phase factor. And the good thing here is that if instead of isotropic spaces, we take totally singular spaces, then the good properties that we had are maintained. So if W is a totally singular space, a dimensional space, then the n-qubit space is a representation, and is still a direct sum of the InGen spaces, which will have dimension 2 to the n-L. Even the theory that helped us to find correctable subspaces still works. When isotropic spaces are changing but totally singular spaces, everything is working well. And something even better is that this proposition is actually the same that we had before, because the stabilizer group is a totally singular group. So then with a simple theory, and in my opinion, a more beautiful theory, we managed to reach to the same result that we use in practice to find correctable subspaces. So as a conclusion of this little talk, we see that if we restrict to the real errors, we do not need the complex order to correct them. And we can conclude too that the theory of stabilizer group can find its basis in orthogonal geometry that is expressed naturally with real errors. So that was everything that I want to talk with you. Thanks for your attention. In the description of the video is going to be my email and some bibliography. Thank you very much.